All right, welcome everyone. Today we're going to start our next major unit of material, and that's going to be sequences and series. So in today's lesson, we're going to introduce the definition of a sequence. We're going to look at some different types of notation, the way we kind of write down a sequence, and just see a few examples of how to visualize a sequence graphically. So by the end of this lesson, you're going to be able to write out the first few terms of a sequence given the general term A sub n. All right, so let's get into it. First, what is a sequence? Let's define it. And it's actually just a function. It's a function whose domain is the set of positive integers. So usually n greater than or equal to 1. We're going to see we can relax this a little bit. But for right now, the definition of a sequence, it's just a function, and the domain of that function is the set of positive integers. All right, so how do we actually think of a sequence, though? We tend to think of it more as an infinite list. So, and with that infinite list, it's written in a specific order. So when we write down a sequence, we start with the first term, go to the second term, the third term, so on. And then we have our nth general term. So there's a specific order going on here with a sequence. We have the first term, we have the second term, third term, and so on. So there's a specific order. And then we have our nth general term here. So the key word here is order. There's an order to this. So there's a first term, a second term, third term, and so on. And for our purposes, we're going to be thinking of them as an infinite list. Now, technically speaking, we could have a sequence with a finite number of terms. But for our course, we're going to be looking at sequences that are infinite. Another way to think of this is if we relate it back to function notation, we can really just think of every term here in our sequence as just a function value. So for instance, if we wanted to, we could think of this first term as just being what we get when we plug the number 1 into our function. We know a sequence is a function, so let's plug 1 into that function. A sub 2, our second term, is just what we get when we plug the number 2 into our function, and so on. So it's helpful to keep that function idea in our minds as we go forward. It's really just a function where we're plugging in integers. But for the most part, we're going to be thinking about this as an infinite list. All right, so what is our general notation here? We have a few ways that we commonly use to represent a sequence. Two we're going to be using primarily is where we use these curly brackets. So that's normally we use these curly brackets to indicate a sequence. And then we just write out the first few terms. And then we put the dots there to indicate that it continues. It's an infinite list. So this is helpful to kind of get an idea of what the terms of our sequence are doing. It helps to write it out sometimes. So this will be something we do. We write out the first few terms. Well, sometimes we want to know what the actual formula is for our function. And so this is where we write out, another way to do this is to write out the formula for that nth general term. And that's what we're seeing here. We see inside here, this is going to be like a formula that we can just plug into. It's kind of our function formula here. So this is just the nth general term, A sub n. And again, we're using curly brackets to denote that this is going to be a sequence. Now we have a little bit more here. We have a little bit of a description for what n is. So a lot of times we're going to think of n, well, it really is, it's an index. So we normally use n to indicate our index. We also sometimes use I. So you might see a sequence written out where we have i's instead of n's. So n is normally our first choice, but a lot of times we also use I as well. And so what this is saying, this n equals 1, this is just telling us what integer our index is starting at. So that n equals 1 is just our starting index value. So we start at n equals 1, and then the sequence just continues and goes on, forever. So we're going to be dealing, again, with infinite sequences here. All right, so these are our two kind of types of notation. Write out the first few terms, or write out the general term and have that as your sort of your formula, and then just indicate where your index starts. And kind of our default position here is we're going to be starting with n equals 1. All right, let's just try an example. Here we're given a sequence, and we're given a sequence where we're given the nth general term. So our sequence, the formula for this sequence is 3n over 2n minus 1. Our index is starting at n equals 1, and then it goes on from there. And what we're going to do is we're going to just write out the first 4 terms of this sequence. All right, so what are the first 4 terms going to be? Well, we're starting with index 1. So we're going to start with n equals 1. Then we're just going to go up from there. So then we're going to look at n equals 2, n equals 3, and n equals 4. And we're just going to take these integer values and we're going to plug them into this formula. So again, it's helpful to think of a sequence as really just a function where we're plugging in positive integers and into this formula. So we're going to plug each of these in. And why are we going from n equals 1 up to n equals 4? Well, our starting index here is starting at n equals 1, and we just want the first 4 terms. So first term, second term, third term, fourth term. So we plug these in. So let's plug n equals 1 into this function. We get 3 times 1 over 2 times 1 minus 1. And if we clean that up, we get 3 on the top. And we get 2 minus 1, so 1 on the bottom. And then just simplifying, we get 3. So really, we're just evaluating a function a few times here. All right, let's do it again. Now let's plug n equals 2 in. So we go to our formula here. Wherever we see an n, change that to a 2. We're just evaluating a function. We've done this before. Not too bad. So 3 times 2 over 2 times 2 minus 1. And what do we get? Well, we get 6 on the top, and we get 4 minus 1, or 3, in the denominator, and that ends up just being 2. And I'm going to give myself a little more room here. All right, so let's plug in 3 now. So we're just going to plug 3 in. Wherever we see an n, plug 3. So we get 3 times 3 over 2 times 3 minus 1, which is 9 over 5. So 6 minus 1 ends up giving us 9 over 5. And then finally, we go to our last one. We plug that in. And what do we get? We get 3 times 4 over, and let me just do this off. Ran out of room a little bit. We'll do n equals 4 over here. And let's plug in. So we're just, again, going up to our formula here. Wherever we see an n, plug in 4. So we get 3 times 4 on the top over 2 times 4 minus 1 in the denominator. And simplifying, we get 12 over 8 minus 1, which is 7. All right, so there we go. We have, what do we have? We have the individual terms of our sequence here. So let's just write it out. Let's write out the first 4 terms of our sequence. So another way to indicate this sequence is, like we said, just writing out the first few terms. So 3 is our first term, so it has to go. N equals 1, that's our first term, so that's what we put first. N equals 2 is going to give us our second term, so that was 2. N equals 3 gives us our third term, so that's going to be 9 over 5. And then finally 12 over 7. And then we put dots in our curly bracket there. That's not a very good curly bracket. Maybe that's a little better. To indicate that the sequence keeps going. All right, so really just writing out the first few terms of a sequence comes down to just plugging numbers, plugging integers into a formula and evaluating. Not too bad. Let's try another example. All right, so let's look at example 2. Again, we have another sequence here where we're given the nth general term. We're going to write out the first 4 terms of this sequence. Now, you might be looking here, and you might be thinking, oh boy, our index is starting at n equals 3, and that's okay. So we can kind of relax things. We can generalize things a little bit. So we can generalize the idea of sequences so that our index n starts at values other than n equals 1. So we might start a little bit bigger than n equals 1. We might start with 0, just other starting index values, and that's fine. We can still talk about a sequence then. So sometimes it is helpful for a formula or just what's going on to start with a different starting index value. Perfectly fine to do this. So in this case, we're going to be starting with 3. So we want to write out the first 4 terms of this sequence. So that means we're going to start with n equals 3. And then we're going to go for the 4. We're going to go, starting with n equals 3, we're going to write down 4 integers. So here's our first integer. Then we write down our next integer, which is 4. N equals 5. And then n equals 6. So this is going to give us the first 4 terms of our sequence here. All right, so let's go through the same process. We have this nice formula right in here. We're given the nth general term. So really that's just like the formula for our function that we're plugging into. So let's plug 3 in. And what do we get? We get negative 1 cubed times 3 plus 1. And if we simplify that, negative 1 cubed is negative, and then 3 plus 1 is 4. So we end up with negative 4. Let's go to the next one, n equals 4. Plug that in. We get negative 1 to the 4th times 4 plus 1. Negative 1 to an even power is positive. So we just end up with positive 5. Do the same. N equals 5. We're going wherever we see an n, plug in 5. So we end up with negative 1 to the power 5 times 5 plus 1, which now negative 1 raised to an odd power is negative again. So we're back to negative. So we end up with negative 6. And then finally, plug 6 in, we get negative 1 raised to the power 6 times 6 plus 1. And when we have a negative raised to an even power here, it becomes positive. So we just have positive 7. So this is something we're going to be seeing quite a bit here, this negative 1 to the power n term. And notice that's giving us this kind of this alternating negative, positive, negative, positive pattern. So it's going to be helpful to remember -1 raised to an even is just +1. And -1 raised to an odd integer is -1. And so because our numbers here, our index numbers, are going from odd to even to odd to even, that's what's giving us this alternating negative, positive pattern. All right, so let's write down our sequence then, another representation for this sequence. So our first term is where our starting index is, n equals 3. So our first term of our sequence is going to be -4. And then we just write them in increasing order. So the next term is going to be for when n is equal to 4, so 5. And then we write down our next term, which was -6, and then 7. And then we put some dots to indicate that our sequence continues on. All right, so that's really it. Just plugging in, and we see that we can relax our starting index value here. Perfectly fine to do this. All right, another example. Let's make things a little bit more interesting. Let's introduce this gadget, and you may have seen this already in other math courses, but we're going to be using this quite a bit in the upcoming sections. And this is a factorial. So this is n factorial. And let's look at the definition. So what is n factorial? So a way to think of it is you start with the number you see there, n, and you just start multiplying all of the previous integers together until you get down to 1. So you start with n, then you go to n minus 1, then you go to n minus 2, and you keep going until you get to 3, until you get to 2, and you get to 1, and you multiply all of them together. So n factorial usually is a very, if n gets big, n factorial gets really big because we're multiplying a whole bunch of terms together here. And we do usually make one kind of distinction here. So there is a special case, and it's going to be helpful to use this in later sections. And that's 0 factorial. So normally this is defined, you can see how it's defined for n equals 1, n equals 2. So the positive integers. We will have occasion to talk about 0 factorial. And so we're going to go with the we're just going to say that's equal to 1. And we'll see why that's going to be helpful in some later lessons. So we're just going to say this is equal to 1. That's what we're going to use. All right. So here's a sequence. Again, we're given the nth general term, so we're given the formula. But now when we look at this, we're going to start at n equals 0. And we're going to write out the first 4 terms of this sequence. So again, let's go through it. We're going to start with n equals 0. That's our starting index. Then go to the next integer. So we're going to plug in n equals 1. Then go to the next integer after that. So we'd want to do n equals 2. And then finally, we would want to consider n equals 3. So we want to go through, we want the first 4 terms. So we start with 0, and then we just increase from there until we have 4 n values. All right, so let's kind of do what we've been doing. Let's start with n equals 0, plug it into our formula. So we get 2 to the 0 over 0 factorial. And when we do this, 2 to the 0 is just 1. And 0 factorial is also, by our special case over here, is also 1. So our first term is 1. Let's do the same thing. Now let's go to the next term. So n equals 1. Let's plug this in to our formula. So we end up with 2 to the power 1 divided by 1 factorial. And what is 2 to the power 1? Well, that's just 2. And what is 1 factorial? Well, 1 factorial, if we go to our definition, you start with whatever integer you see there. So you start with n in general. We're going to start with 1, and then you just start multiplying until you get down to 1. So 1 factorial is just 1. So we end up with 2 as our second term. All right, let's go to our third term, which corresponds to n equals 2. We're going to plug that in. So let's plug it into this formula. So we're going to end up with 2 squared over 2 factorial. And let's actually see what this is going to be equal to. So 2 squared is 4. And then what is 2 factorial? Well, we're going to start with the integer we see there, which is 2. And we're just going to start multiplying until we get down to 1. So it'll be 2 times 1. And that ends up simplifying also to 2. All right, what about n equals 3? Let's plug this in. So we're going to get 2 cubed, 2 raised to the power 3, because, again, we see n in the exponent there. And this will be all over 3 factorial. So what do we get if we multiply out the numerator? We get 8. And then what is our denominator? Well, we're going to start with 3. And then we're just going to start multiplying integers until we get down to 1. So it'll be times 2 times 1. So that's 3 factorial. And what is that? It's 6. And so we end up simplifying. This ends up simplifying to just 4 over 3. So if we wanted to write out another representation for this sequence, our first term is 1, so we put that first. And then our second term is 2. Our third term is 2, and then our fourth term is 4 over 3. And then we could put dots to indicate that it continues on. Now for the fun of it, let's just, what would be 4 factorial here? Just to get a little bit more practice working with these factorials. Well, we're going to start with 4, and then we're just going to start multiplying integers until we get down to 1. So then we'll multiply 3, down to 2, down to 1. Or another way to think of factorials is you start with 1, and then you start multiplying until you get up to that number that you see. So 2 times 3 times 4, and I see that I've got up to 4, and I'm doing 4 factorial, so I would stop. So you can either start with that number and kind of multiply until you get down to 1, or if you want, you could start with 1 and multiply up until you get up to 4. You can think of it either way. All right, so that's a little example there showing how to work with factorials, and we'll be seeing these again. All right, now sometimes we'll have the first few terms of the sequence and we want to actually find the formula for our general term. So that's what we're going to be doing here. We're going to be finding the formula for our general term a sub n. And we're going to suppose kind of our default position. If it's not indicated, the default position is that we start with index n equals 1. All right, so we're trying to figure out the formula for the general term a sub n given just a few different function values. So really what we're trying to do is we're trying to figure out the pattern. And this is notoriously difficult. Being able to figure out a pattern here from the first few terms is going to be difficult, but we can do it. And there's in some cases. And there's some strategies to try. So when you look at this, when we have the first few terms of our sequence here, negative 3 over 4 is our first term, 9 over 5 is our second, negative 27 over 6 is our third term, and then 81 over 7 is our fourth term. When you look at this, you want to kind of just break it apart as much as you can. So when we look at this, I see fractions everywhere. So try to identify if there's a pattern going on for those pieces in the numerator. Same thing. I see denominators. So see if you can identify the pattern for what's happening in the denominators. So try to break things apart. I also see some negatives. I go negative, then I go positive, then I go negative, then I'm back to positive. So that might be the first thing just to kind of start with. Is we've seen this in one of our earlier examples here. When we have this alternating pattern, negative, positive, negative, positive, we've seen something that gives us that alternating pattern. -1 raised to the power n. Now, sometimes this doesn't always give us the right pattern. So there are some other choices that we commonly use. -1 raised to the n plus 1. Maybe -1 raised to the n minus 1, whichever is more convenient there. And for the most part, these give us, all the different cases. And we know we're starting with n equals 1. So let's think about what pattern we get from each of these if we start with index n equals 1. So let's think about what pattern do we get from -1 raised to the power n. Well, when I start with n equals 1, I'm going to have -1 raised to an odd power. So that gives me a negative. Then when I go to n equals 2, the next term in our sequence here, I'm going to have -1 squared, which is going to be positive. And then you can continue on. We're going to end up with actually the correct pattern, negative, positive, negative, positive. Just out of curiosity, let's see what happens when we look at -1 raised to the n plus 1. And for that matter, -1 raised to the n minus 1. These are going to give us the same thing. If I plug 1 into either of these, I'm going to end up with -1 raised to an even power. So that's going to be positive. Then if I plug n equals 2 in, I'm going to end up with -1 raised to either 3 or 1, so an odd power. So I get negative. Then when I plug n equals 3 in, I'm going to have an even power again, so I'm back to positive, and then negative. So we're going to see in our actual sequence, we have that negative, positive pattern. So we're going to go with the piece that matches that pattern. So -1 raised to the power n. All right, so that's kind of the where to start with this. So identify, kind of break this apart. And that's the first thing we saw. All right, so we're going to use -1 in our general formula. The next thing we're going to try is we're just going to try kind of looking at the numerator separately. We'll look at the denominator separately and see if we can figure out a pattern for those. So let's start with the numerator. And again, it's going to be helpful to kind of, we're starting with n equals 1. So then the next term is going to correspond to n equals 2, then n equals 3, then n equals 4. So it's helpful to write those kind of positions out because we're trying to figure out a formula for how does this fraction match up with this n value. So let's write out a little table. N equals 1, n equals 2, n equals 3, n equals 4 for all of the pieces in our numerator. So what's our first numerator? It's 3. Then our second numerator is 9. Then 27, and then 81. And usually, to help identify the pattern, and maybe you already see it, but just trying to develop some strategies here to help you identify the pattern. And usually what can be helpful is to factor. So try to factor each of these. So if we do that here, 3 is, it's just 3. 9, that actually factors. That's going to be 3 squared. 27, that factors. That's going to be 3 cubed. And then 81 also factors. That's 3 to the power 4. So notice that our first fraction, or our first numerator, starts with n equals 1, and there's really a hidden 1 in our exponent here. Our next numerator corresponded to n equals 2, and we have a 2 in our numerator, or in our exponent there. So it's 3 squared. Then we have n equals 3 for our next term, and we have raised to the power 3 for our term there. And then 4. And we have, for our fourth term, we have raised to the power 4. So you can kind of see what's going on here. So the general term would have 3 to the power n in our numerator. So our first one had 3 to the power 1. Our second one had 3 squared. Our third one had 3 raised to the power 3. And our fourth one had 3 raised to the power 4. So in general, the nth one would be 3 raised to the power n. Now let's consider our denominator. What's going on with our denominator? So again, it's helpful to kind of write out the n terms. So n equals 1, n equals 2. Do a little table if you want. And just look at the pieces in the denominator. So 4, 5, 6, and 7. And you're trying to identify, how do these numbers match up with the n values? So one thing to look for, we don't see the numbers getting drastically bigger here like we did with the numerator. They're just increasing kind of by, looks like by 1 each time. So notice that it's getting all excited here. So notice that, really we're just increasing by 1 each time. So when you see that kind of thing, you want to look at what's the difference between the value here and our n value. So what's the difference? So our actual piece of our sequence here is 4, and that's 3 more. It's 3 larger than n equals 1. So the 1 here, it comes from our n value. So we see that in this case, 4 is equal to 3 plus 1. Now let's kind of do that analysis for 5, and we see that 5 is 3 more than 2. So we're just looking at the difference between the actual piece of our sequence and the corresponding n value. So 5 is 3 more than our index 2 value here. And then same thing for 6. And so we're starting to see the pattern. And same thing for 7. 7 is 3 more than our n value. And so in each of these, the difference stays the same. So if we were to try to identify a pattern off of this, the general term, what would it be? Well, we see our n value. So here's our n value in each of these. N value 1 plus 3. N value 2 plus 3. N value 3 plus 3. N value 4 plus 3. So our general term is going to be our n value plus 3. All right, so, and that really takes care of everything. So we went through this with some detail here because these can get a little tricky. So identifying these patterns can be a little tricky. So we're just kind of developing some strategies here. All right, so what did we find for our sequence? Well, to get that alternating pattern, we had -1 raised to the power n. And then for our fraction, our numerator we said was going to be 3 to the power n. And our denominator we said was going to be n plus 3. And we use our curly brackets. And now we've written our general term. So we're starting with n equals 1, and we're going from there. All right, so just some strategies. You might do this completely different, and that's fine. So these are just some things to try. Try factoring. Try looking for differences between the values and the index values. It's going to take a little bit of scratch work to identify these patterns. But we got it. All right. One last thing. How do we picture sequences? Well, we can kind of graph them. And what we're seeing here is we're seeing a few things. So this is our first example that we looked at. The sequence 3 times n over 2n minus 1 from n equals 1 to infinity. And we can just plot these as discrete points on our xy plane. So for instance, the first point here corresponds to n value 1, and it's just our sequence value, a1. Then our second point here is when n is equal to 2, and that is whatever our sequence value was, a2. We did that in example 1. Won't rewrite it here. And then so on. So this would be like the n value is 3, and then it would be sequence value a3. And then we can keep plotting points. So this is just a way to kind of visualize a sequence. It's just discrete points on the xy plane. Now, what is this curve here? We do see a curve. The curve is actually the function f of x equal to 3x 2x over 2x minus 1. So this is going to be a distinction that we will kind of come back to. Generally, when we use n, we're thinking of n as an integer. So it's a discrete value here. We're getting these discrete points. When we think of a function 3x over 2x minus 1, we're thinking of x as a real number. So when we plot the graph of 3x over 2x minus 1, we're plotting it for all real numbers, so we get all of the points on the curve. With a sequence, we're only getting some of the points on that curve, corresponding to those integer values. So this is one way to picture it. We can picture it on the xy plane. Another way that's helpful is to just plot each term of our sequence on the number line. And again, same, here we have it kind of plotted out for the first sequence we looked at in example 1, 3n over 2n minus 1. And we've just plotted our sequence values on the number line. And so for instance, here, this point corresponds to our first term of our sequence. So we found it was 3. This point here corresponds to the second term of our sequence, a2. And then so on. There's the third term. And they don't have to necessarily go decreasing. They can be all over. They can be kind of scattered around. But it happens for this sequence that they all kind of tend to decrease. So this is another helpful way to picture what's going on with a sequence plotted on a number line. And where we're going to go next time, so spoiler, we're bringing back limits. You can see these points. So we have a few more terms here for our sequence plotted, and you can see that they're kind of bunching together. What does it mean when they're bunching together? Well, we're going to be talking about limits again. We're going to be talking about convergence sequences and divergence sequences. And so this idea of when we see our sequence, the terms start bunching together, well, we want to investigate that. We want to know specifically, why are we seeing this bunching behavior? And we're going to be talking about limits. So if we plot it on a number line, we might see them all kind of bunched together. If we go back to our graph, while we're plotting the points, what we might see in this case is a horizontal asymptote. And the horizontal asymptote is when we're talking about just that real value function. But it looks like all of these points are getting closer and closer to that line, that horizontal line. So again, when we see that kind of behavior visually, really what's going on is it's some kind of limit that we're really interested in. So we're going to talk about that next time. All right, so we'll see you then. Bye-bye.